anyway. All right, on that cheery note, let's begin class. I'll begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for these students. Just ask you bless our work. Help us to glorify you in what we do, and I just pray that you'd encourage the students if they're struggling, just to keep up the work, and just remember the course is not a sprint, it's a marathon, but we can all do it if we just put our mind to it, Lord. In your name I pray, Lord Jesus. Amen. And I believe that, like, I can't really say that in good conscience in like Calculus 1. There are ways people can get into Calculus 1 where, it may not go well. But for the most part, you guys have suffered through Calculus 2, so, this is just the next step, right? It's just the next step in the education, and like, it's not really harder. I don't think it's harder than Calculus 2. It's different. Like, you're going to have to stretch different muscles in here. I think the main thing that's really, really different than Calculus 2 is the need for visualization in this course, right? There's a certain amount of visualization, which just really wasn't hardly an issue at all in Calculus 2, right? So, I said I was going to start calculus today, but it is on my mind. I need to talk about spherical coordinates at least a little bit before I start the calculus, in part because I have after all assigned you a token homework problem at the start of mission 2 about these things, so it'd be kind of rude to not at least do a little bit of discussion about it. So let me just draw the picture, that's the main thing, and talk about the convention here. So spherical coordinates are the natural coordinates to talk about with respect to like a, yeah.
Are you going to pass out mission 2 and we just go to the library and print it ourselves?
Oh yeah, you just go to the library and print it. Yeah, that's a good question. No, I don't usually print emissions. I suppose I could print them for you guys because it's just like 3 pages each time, right? So if you guys want me to, I can. No one will notice. Let me print missions for you guys. Shh. All right. Don't tell my other classes. There is no earthly way I could do this for college algebra because there I leave them like white space to work. So their missions are like 20 pages times 80 students. There's no budget for that. But I think we can put you guys in the budget. All right, so spherical coordinates. So tomorrow I should give them to you, okay? Is that good? Okay. So spherical coordinates, if we take a point, right, we can talk about the spherical coordinates in the following way. So spherical coordinates is at this point right here, which would be x, y, z. And I just draw it in this quadrant because it's where my pictures are nicest. But that point, of course, you can drop down, right? And there's a point down here. What's that point? In the projection into the xy plane, it's what? It's x, y, 0, all right? And then you can draw this line like that, right? And you can project back to here. That's supposed to be parallel to the y-axis, right? So this right here would be y. This right here would be x, right? This distance there. I mean, this point specifically would be x, 0, 0, right? For what it's worth. And so when you guys talk about polar coordinates, you already have a definition of standard angle, right? It sweeps in the counterclockwise sense off the positive x-axis. So that angle still makes sense here if you just focus on this down here, right? On this blue triangle down here. There's you can just do polar coordinates down there, right? So this angle is theta. We still think of it as theta, right? And if this was r, and it's still called r, of course we've got x is equal to r cosine theta, and we've got y is equal to r sine theta. That's just polar coordinates actually, right? But if you throw in a z, this becomes the cylindrical coordinate system, right? So cylindrical coordinates are formed by taking the polar coordinate system of the projection of the point into the xy plane and just marrying it with z. Spherical coordinates are a little bit different. We have to introduce a new angle. Now, I should mention here, what's the range of theta? I mean, choices vary, but here's a good choice. You can go 0 to 2 pi. That is not rigorously enforced. Sometimes we go like minus pi to pi. It depends on what suits our purposes, right? You guys remember in Calculus 2, sometimes you do integration over theta, where it just made more sense to integrate from like minus pi over 2 to pi over 2 as opposed to 0 to pi over 2 and 3 pi over 2 to 2 pi, which would be like geometrically equivalent. All right, so there's that issue. Now, here's the new one. The angle off the positive z-axis, well, that's this right here, right? This is so-called phi, all right? And I believe, well, anyway, so that angle would be defined by, you know, if you were to take the, for example, z hat vector, which would be like this, right? And you were to ask, what's the angle between, you know, this, if I call this the position vector, for the sake of discussion, x, y, z, r vector dot z hat, right, would be equal to the length of the position vector times the cosine of that angle, right? But this is z, and this is, well, what's the length of this black line here? We give it a name. We call it rho for the spherical radius. So it would be rho cosine phi. Now that is the first of the spherical coordinate formulas. Well, not the first, the last, I suppose. But as it turns out for this lecture, the last will be first, right? It's biblical. Don't say there's no biblical integration. It's everywhere. You just got to look for it. But if that's rho, right? That's rho. And that's, so these lines are parallel, right? So this is a line which is going through two parallel lines. So that makes this an alternate interior line, which by geometry makes this phi as well. And if that's phi as well, you notice that we've got the hypotenuse of this vertical, soon-to-be green triangle. The hypotenuse of this vertical, in the sense of z being up, right? This triangle right here, it's a right triangle. Here's the 90-degree angle down here, right? 90-degree angle. The hypotenuse is rho. The opposite side is r. So we just discovered that this over here is rho cosine phi. That's this side here. That's equal to z. And down here, what's r equal to? Well, it's equal to rho sine phi. Right? Rho sine phi is the relation between the spherical radius and the polar radius, right? Spherical radius is distance from the origin. Polar radius is just distance to the z-axis. These are different, right? So, but now that I have foolishly written, this is poor choice on my part, right? This needs to be, sorry about that, guys. But if you just put in what the r is, what you got? You got rho sine phi cosine theta, and you've got rho sine phi sine theta. These are the standard, right here, these are the standard math spherical coordinates. There are at least 3 popular choices of spherical coordinates. This is just one. In engineering, annoyingly, and physics also, they switch the meaning of theta and phi. And sometimes they use an r instead of a rho. And for the r, they use an s typically, at least in my physics books. So these notations are not universal, but this is the notation we, by default, use in here for spherical coordinates. All right? There's another system of spherical coordinates where the angle like phi sweeps up off the xy plane. That's actually a very nice choice. It gives really cool formulas, but that's the only place I've seen that is in a differential geometry book, but by Barrett O'Neill. But these are the spherical coordinates formulas. So just to emphasize here, what's the formula for rho? Rho is the square root of x squared plus y squared plus z squared. In contrast, r is the square root of x squared plus y squared. What else can I tell you? The tangent of theta, well, you already know this one. It's y over x, right? That's still true for spherical coordinates. On the other hand, the cosine of phi is equal to z over rho. That's true. And this right here, r, is equal to rho sine phi. This formula right here is a bridge between spherical and cylindrical coordinates. So these are the big ones. I'll give you one example and then we'll go on. Oh man, well, this is actually a nice marker. That's like the most dark green marker I have. I should save this. This is important. It's about impossible to find a decent green marker. Example 1. So what if I have the point, let's say 1, minus 1, I don't know, 3. Suppose these are the Cartesian coordinates of a point. My question is, what are the spherical and what are the cylindrical coordinates of this point? So find the cylindrical and find cylindrical and spherical coordinates. How do we do that? So I would start by, let's find the cylindrical coordinates. That's pretty easy, right? As it goes. So if I look at cylindrical coordinates, I can think about, you know, if I picture 1 minus 1, where's that? That's like here, right? If I just think about the two-dimensional vector, 1 minus 1, for a second, I can think about finding the standard angle of that vector. That's the same as the standard angle for the spherical coordinates, right? And what is that angle? You can see this theta equals to what? What's that? 45 degrees, but theta is measured how? It's measured counterclockwise from the positive x-axis, right? So if you want to say 45 degrees, you got to say minus 45 degrees, right? But we try to think in radians in here, I guess, so I should probably say theta is minus pi over 4. But yeah, 45 degrees is also be fine. That's just a choice of, you know, I don't know, it's like, is a tomato a vegetable? I'm pretty sure it is. Anyway, I don't care about these technical definitions of fruit. My question is really just, would you make it into a dessert? If you're serving tomato as a dessert, like, it's just not right. I feel like. You can?
I'm sure there's some way.
There's some way? You put enough sugar in it? Sure, yeah. But, all right. It's like, here, have a popsicle. Oh, what flavor is it? It's tomato. It's like, oh, no. Oh, okay. So theta equals pi over 4, and what's the radius? The cylindrical radius is square root of, you know, 1 squared plus 1 squared, because the minus gets eaten, right? So the cylindrical radius is just square root of 2. All right, so cylindrical coordinates are r equals square root of 2, theta equals minus pi over 4, and z. What is z? 3, right? What's the spherical coordinates for this point? I'll do that in blue. I'm going to get rid of this marker. Well, I tried. Anyway, so spherical coordinates, so that's the cylindrical. Check. Spherical. Good news. Theta is still theta, so it's still minus pi over 4. So we're not like, oh, thank you. We don't diabolically like use a different theta for spherical and for cylindricals. That would be evil, right? Same theta. Yay. What's phi? Phi is equal to the inverse cosine of your z. Let's see, so if this is the formula for z, what's the formula for phi? I got cosine phi here, right? So what's phi equal to?
Inverse cosine of z over rho.
Inverse cosine of z over rho. You're like, but hold on a second. It can't just be that easy. It can't just be so simple that you find the angle by just using a single inverse trigonometric function. Right? Because we've been conditioned to worry about the theta, right? Because you know full well that some of you got the problem wrong on the quiz, the problem that I put you in quadrant 3 where you can't use inverse tangent, right? And you got to think through it. It was like 225 degrees because it was actually down here in the quiz, right? So you got to go like 180 plus another 45, like that was that problem. I know at least, I know you guys, some of you got that wrong, right? So like the angle of polar coordinates, right? It requires analysis, right? You got to think about which quadrant you're in, blah, blah, blah. But this angle, the angle off the z-axis, phi as we call it, it's much easier. It's just inverse cosine of z over rho, which in this case is 3 over what? Oh, I guess I need to find rho. What was rho equal to? Square root of 1 squared plus 1 squared plus 3 squared, which is, 9. So apparently rho is the square root of 11. So we've got 3 over square root of 11. And so I don't know what that is, but And this is why you need a calculator, right? You should have a calculator here for future quizzes. If you didn't this time, do get a calculator because you need one. Because I would like to have numbers here. Square root of 11. Let's see. At the moment, I'm in degree mode, so we'll content ourselves with the degrees. This is 25.24 degrees, approximately. All right. So by the way, of course, we can naturally limit the theta to range over any 2 pi period, right? How about the phi? What's the range of phi? They're not the same. The angle off the z-axis, so the z-axis is phi equals to 0. What's the negative z-axis? That's 180 for phi. And as you sweep from 0 to 180, that's everything. So like the xy plane would be 90 degrees for phi. All right, so you basically just sweep down like that. So 0 less than or equal to phi less than or equal to pi if we're doing radians, or 180 degrees if we're doing, well, degrees. Any questions? So there you go. I just wanted to give you a slightly less frantic introduction to these coordinate systems. We will come back to them and use them as the course progresses. This is just kind of a, hey, get to know you. This is what they are. All right, and you got a token homework problem or two on them. Now you can use these things to create parameterizations of things. Like let's just one example like that, and then I really will stop and do calculus, I promise. What if you wanted to parameterize a cone? Like in Cartesian variables, if I wanted to talk about this cone, it would be kind of, I don't know if I'd know where to start. Well, I mean, I guess I know, but this cone would be kind of a drag, right? Suppose this is the cone z squared equals to x squared plus y squared. I believe that's a cone. What does that look like in spherical coordinates? Well, we can convert to spherical coordinates a few different ways. One way is to notice that this is r squared, right? And so I've got rho cosine phi, quantity squared, that's my z. And then rho sine phi, quantity squared, that's my r, right? So we get cosine squared phi equals to sine squared phi because we got a rho squared on both sides that cancel out, right? So apparently the equation for a cone just depends on what? In this case, I've got, cosine phi is equal to plus or minus sine phi, but this just tells me that sine phi equals to cosine phi because 0 is less than phi is less than pi. So in that context, sine is positive, and okay. Well, anyway, let me not quibble over this too much. It's really not the point of this lecture. My point to you is you can, let me just stop a step earlier and just point out to you, what's the solution here? Oh, I'm an idiot. There are two things. So let's just say that z is positive, right? I shouldn't deny the math. The math was telling me what? The math was telling me, and I was in denial for a second, but the math is telling me sine phi is plus or minus sine phi, right? The reason for that is the equation z squared equals x squared plus y squared. Their solutions either for plus z or minus z. Like the minus z is the cone below. Like I said, it's a double cone. So the minus z is actually this solution set, it's also down here, right? But I don't want to really, I'm trying to throw that out for the current discussion, all right? So because we're throwing this out, we just get cosine phi equals to sine phi, which is to say that phi equals to, well, pi over 4, right? That's when you get sine and cosine are equal with an angle between 0 and 90 degrees, right? So the equation for the cone is very silly. It's just phi equals to pi over 4. That's the equation for the cone in spherical coordinates. So this right here is equivalent to this right here paired with what? Paired with that. So, these two things are that. What's a parameterization of the cone? So the way to write down a parameterization of the cone is to use spherical coordinates. In particular, if I want to parameterize the cone, I can use, what's the natural choice of, natural choice is to use spherical coordinates, right? But in spherical coordinates, what's happening for the cone? One of the coordinates is frozen, right? So we can just literally use the spherical coordinate formulas with phi set to constant. What's that leave you? It leaves you with rho and theta, right? So I can look at this parameterized by rho and theta. In particular, the parametric formulas are rho cosine theta sine pi over 4, rho sine theta sine pi over 4, and rho cosine pi over 4. There you go. That is a parameterization of the cone. So we can use like spherical coordinates to get to like obtain parameterizations of, well, they're most natural for obtaining parameterizations of spheres, of cylinders, right? If you fix theta equal to a constant, you get like a half plane off the z-axis. These are particularly nice surfaces for these coordinate systems, yeah?
When you say parameterization, does that always refer to a Cartesian system?
A parameterization, what that is we're giving a pair of parameters which uniquely fix each point on the surface we're trying to parameterize.
But is that always a Cartesian system, or could you do parameterizations in spherical?
Could you do yeah, you could yes, indeed, you could parameterize. You could give instructions for how to parameterize the spherical coordinates and then plug those into the spherical coordinate formulas to find the parameterization in the Cartesian. But pretty much in here we just look at Cartesian. We want formulas for the Cartesian, the x, y, z coordinates for the parameterization. So he's talking about in Calculus 2, there's a place where we talk about like polar parameterizations. We don't do that. We don't really explore that too much in here. I mean, it is something you can do. Anyway, I shut up, yeah. All right, I now have spent entirely too much time on spherical coordinates today. My apologies. You guys, of course, want me to do calculus, right? So I thought I was going to spend 10 minutes on this today. Look what's happened. So sad. All right, I'm going to start the video again.